Hello, good morning students. So today let's take up a class on substitution reactions. So last class we have to take what are the substitution reactions and what are the processes of substitution reactions. So substitution reactions are those reactions which one group attached to carbon may be replaced by another group in another group. So I write down here. So one group attached to carbon may be replaced by another group atom, by another group or atom in. So this can be, so this is known as, you can say this is the substitution reactions. So I'm repeating again, substitution reactions may be discussed as one group attached to carbon may be replaced by another group. So it is known as substitution reactions. So there are three processes, there are three ways or three processes for giving these substitution reactions. Three processes of substitution reactions. Okay, there are three processes for undergoing these substitution reactions. So let's say one by one. First one is by synchronous concerted. Synchronous means concerted synchronous substitution. See, the one process is, the first one is by synchronous substitution. Second one is by elimination followed by addition. By elimination followed by addition. Okay. Third one is by addition followed by elimination. By addition followed by elimination. So these are three processes for undergoing the substitution reactions. So the last one applies to unsaturated system. Okay, unsaturated carbon, unsaturated carbon or system. So I'm repeating again. Substitution reactions may be defined when one group attached to carbon is replaced by another group or atom. So there are three processes for substitution reactions to undergo substitution reactions. First one is synchronous substitution, and second one is by elimination followed by addition, and third one is by addition followed by elimination. So the last one is always applies to unsaturated carbon system. So let's take one by one. So let's first take up this one, synchronous substitution reaction. Okay, synchronous substitution reactions. So first one, let's take up synchronous. This is a concerted one. Synchronous substitution reactions. Okay, so here reactions are simultaneously concerted system, simultaneously leaving group and attacking groups are simultaneous. So here this is a concerted system. So let's here here you can have two types. If the reagent is a nucleophile, then we can have nucleophilic substitution reaction. If the reagent is an electrophile, then we can have electrophilic substitution reaction. So I write down here, the reagent will be, for the system of synchronous substitution reaction, the reagent may be a nucleophile. So you can say it is a nucleophilic substitution reactions. For this case, constructed system, we have SN2 reaction, or you can have or an nucleophile. That can be a nucleophile, nucleophilic, or you can say nucleophile. Nucleophile, you can have SN2 concentration, and then you can have an electrophile. The reagent can be have electrophile. Then we have Sc2. Substitution electrophilic bimolecular here. So generally atoms do not substitute directly at carbon. So okay, now I'm repeating again that synchronous substitution reactions can be divided into two systems where it depends on the nature of the reagent. If the reagent is nucleophile, then we have nucleophilic substitution reaction. If the reagent is electrophile, then we have the electrophilic substitution reactions. So depending on the nature of the attack, the substitution reaction may be divided into three types. So depending on the nature of attacking group, either nucleophile or electrophile of the attacking group, depending on the nature of the attacking group or atom. Attacking group substitution may be divided, maybe classified as follows. Maybe classified as follows. Okay. So into three types. First one is SN2. That is substitution nucleophilic bimolecular. Okay. Then another one is second one is Se2. Okay. Substitution electrophilic bimolecular reaction. Okay. And third one is SNI. That is here is substitution nucleophilic internal reaction. So you can have three types of this concerted system in this synchronous substitution reactions. We have three types of system: SN2, SE2, and SN1. They are concerted. Then now let's have the second process of substitution reaction. Second process. Let's take up the second process. There is the elimination followed by addition. Okay, elimination followed by addition. So here, substitution reaction, elimination, first elimination, followed by addition. Okay, followed by addition. So this is the second process of substitution reactions. So when a carbonated group has a strong capacity for departure, the carbonated carbon has a group which has a very strong capacity for departure with the bonding electron pair. Then we have the unimolecular sulfolysis reaction. So let's say I write down here, when a carbon atom is attached to a group which has a strong capacity means good living group. Capacity means for departure means a strong capacity for departure. You can say a good living group departure with the bonding pair electrons with a negative charge. Okay, bonding electron pair. Then we have a unimolecular sulfolysis reactions or sulfolysis. It is generally called SN1. Okay, substitution nucleophilic unimolecular reaction can occur. Okay. So I'm looking again. So here for elimination followed by addition, we have when a carbon atom is attached to a group with a strong capacity for departure with a bonding electron pair. That is, has a good living group. If the living group has a good living group, then we can have the molecular reactions. So, for example, we can have say CCl, or you can have the C-vital group or R3 groups. Okay, 3 groups. Okay, and first you'll go. This is a good living group. Then we can have this first a carbocation is formed. This one. Click this one. Then we have this one. So it's a good living group. Then go to the first carbocation. This carbocation then again reacts with the nucleophile, say water solubilizes. You can say CH3, CH3, COS. Get the OS too fast, okay. Solubilizes, then lost this proton, then we can have alcohol. CH3, COS. That's vital alcohol, okay. So it's another example for this type of elimination, followed by OS is written here. You cannot see here. OS, okay. So here I'm repeating again. Yeah, elimination first eliminated the living group. It's a good living group is eliminated. Then attacked again. Yes, and attacked by the nucleophile to get this product. Okay. So this is another process. Elimination, first elimination, and followed by addition. Okay. Elimination, followed by addition. So this process is mostly found in SN1. Then now we can have another reactions. Addition followed by elimination. Addition followed by another substitution reaction is addition followed by elimination. So we can have this one. Addition followed by first addition takes place. Elimination. Okay, this is generally found in the unsaturated system. Okay, this type of reaction is found in nucleophilic substitution reaction is found in the unsaturated system. So here benzene and his halogen derivatives can undergo like ethylene, alkynyl halides are inert to nucleophiles in normal conditions. In normal conditions, the aromatic halides, aromatic benzene and the aromatic halides, benzene halide, halides are inert to nucleophile in normal conditions. But in the vigorous condition, they can undergo substitution reactions. So I write down here benzene and its halogen derivatives, means halides, halogen derivatives, like ethylene and alkynyl triple bond, or double bond halides are inert to nucleophiles in normal conditions. Nucleophiles in normal conditions, normal laboratory conditions. But in higher processes, in high vigorous conditions, high pressure or in a high temperature condition, they can undergo they can lead to substitutions. Okay, for example, say phenyl chloride, chlorobenzene reacts with phenol hydroxide in high temperature, and high pressure, 30 degree, and high pressure, then you have this phenol. Okay. Chlorobenzene undergo substitution by OS group in high pressure. So, but if there is introduction of negative the auto or ferra position, good living group, then the rate of the reaction increases. Suppose the introduction of groups, addition of groups of type minus negative type, or at the ortho or para positions, okay, ortho or para positions with respect to the living group, okay. Then the rate of the reactions increases. Rate of reaction increases. Then significantly increases. So reaction takes place in high phase. If there is a mesotype M minus M negative type of this mesomeric type of living groups are present in the ortho or para position. So these are mostly found in negative unsaturated system like benzene or that. So suppose I will write down here another example I will give. Okay, for addition followed by elimination. Okay. So here, say look for example unsaturated system of this type. Okay. So here, first one is okay. First is addition takes place. So here the addition takes place. Then say let's say R negative charge, or here nucleophile, you can say nucleophile attacks. And this is chlorine. Okay, then here nucleophile Cl. Then we have the hydrogen here. Then we have negative charge. Then so addition, then followed by elimination. Okay, like this. So nucleophile. So these are one example I'm giving, general example. So first addition followed by elimination. So addition by nucleophile, then lost the chloride is lost in the living group. Okay. So here is also another example of nucleophile. This nucleophile substitute the chloride. So it is another example of nucleophilic substitution reactions. So these are about the addition followed by elimination. So and this can take place mostly in this nucleophilic reaction, but now we can have electrophilic system also. Addition followed by not only nucleophile, we can go in electrophilic substitution reaction. So it is very common in aromatic system. Electrophilic substitution is very common. Electrophilic system, not nucleophile. Electrophilic substitution at aromatic carbon. So it is very common for this kind, electrophilic. So addition followed by elimination. So for example, say nitration of benzene. So nitration of benzene. So this is like nitric acid and sulfuric acid. So nitration will go to get this nitrobenzene. Okay. So here hydrogen is substituted by the hydrogen is substituted by this nitro. So here it is not nucleophile, it is electrophilic substitution reaction. So it is very common in aromatic system. So here first we have this sulfuric acid, nitric acid to give this nitronium ion plus iso3 positive plus, we will discuss it later on. Okay, so 4. We will discuss this later on. So here this is the electrophile. So it is attached to the benzene ring NO2. So here attacks. So these benzene rings attacks to the attack here. Okay. So you got first intermediate. Cation is of 10. carbocation is often here. Okay, so here. So then loss of this one minus H positive, we got this product. Okay, NO2. So this is the how you got this in mechanism, small mechanism. I will discuss that in detail in the subsequent classes. Okay. So it is another example for addition. So first is addition by electrophile, then followed by elimination of this hydrogen. Okay. So this is the way. This is another example of electrophilic substitution aromatic system. So you can have addition followed by elimination can take place by either addition can take place either by nucleophile or by electrophile. So we discussed these two, but addition by nucleophile is very limited in the case of aromatic system. But in the case of electrophilic substitution reactions, it is common in the aromatic compound here. I am giving example here. Now, so let us discuss first this nucleophilic substitution reaction now. Before coming now, nucleophilic substitution reaction SN1, SN2, SNI. So let's discuss one by one. So now let's discuss nucleophilic substitution reactions. Nucleophilic substitution reactions. So we had discussed earlier. So the substitution reaction can take place by two systems, either by attack by nucleophile or attack by electrophile. So depending on the nature of the attack, we have two systems: nucleophilic substitution reactions and another one electrophilic substitution reactions. So nucleophilic substitution reaction takes place when a nucleophile replaces another group. That is, a nucleophile attacks the substrate, then we have the nucleophilic substitution reactions. So maybe not many alkyl halides, alcohols, ethers may be attacked by this. So there are three features for features of nucleophilic substitution reactions. So let's discuss features of nucleophilic substitution reactions. Nucleophilic substitution reactions. Okay. So we have discussed if the nucleophile attack organic substrate, then we have the nucleophilic substitution reactions. So nucleophilic substitution reaction can take place by three processes. First one is that they are polar reactions. Polar reactions. The nucleophilic substitution reactions are polar, which involve polar reactions, which involve and you can see and electrophile or and a nucleophile. Okay. First one, the nucleophilic substitution reactions are polar reactions which involve an electrophile and a nucleophile. Second one is leaving groove is involved. A leaving groove is involved. Generally highlight a leaving groove is involved, usually a heteroatom, like halide or oxygen heteroatom, like a halogen or an oxygen atom. Okay. So here they involve the reactions are polar reaction and a leaving group is involved. And third case is a leaving group is attached to group is attached to a sp3, not sp2. Okay, attached to an sp3 saturated carbon atom, hybridized saturated carbon atom. Okay, carbon atom. This is the system. That is, a nucleophilic substitution reaction takes place in the saturated system. And another one is a nucleophile other reactant. A nucleophile nucleophile living group, as well as we have one is the living group is involved, another one is a nucleophile is the other reactant. Okay, so we have involved two reactants. One is living group having compound having living group, another one is nucleophile. Then so now these are the features. So I'm repeating again, features of nucleophilic substitution reactions are that they are dipolar reactions which involve a nucleophile and nucleophile, and living group is another one group is living group is involved, and the living group can be attached to an sp3 not unsaturated system, and nucleophile is the carbon atom. Okay. Now we have how it takes place. So let us see what about the living groups. So the features of the living group is that living group should be a weaker base. So weak bases, good bases of living groups are good for these nucleophilic substitution reactions. So good living groups are weak bases. If the living groups are very weak bases, then the reaction is a good living reaction takes place. The reaction takes place very good. That means good living groups are weak bases. So for a substitution to take place, the bond between the carbon and heteroatoms has to break. So whenever the bond between the carbon and heteroatoms to be break, okay. So to break this is the living group X is the living group. The living group should be a weak base. If the weak base, then it undergo nucleophilic reactions. Very good. So here living groups are mostly X will be like halide, bromide, chloride, and iodides are good living group, which are conjugate with because they are the conjugate, which are the conjugate bases of strong bases, conjugate things like that here, which are the conjugate bases of the strong acids like HCl, HBr, HI. Okay, so they are weak bases, so they got a good living groups. So one of the criteria for nucleophilic substitution reaction is that the living groups should be very weak bases. They should be very weak bases. And then what about the nucleophilic? What about the nucleophiles? For the nucleophile, it should be depends on bases, basicity, and polarity. Okay. What about the nucleophilicity? Nucleophilicity depends on basicity and polarizability. Okay. So we have discussed earlier for nucleophilic substitution. For the living group, it should be weak bases. For the good nucleophile, it should depends on basicity and polarizability of the compound. So nucleophiles with a negative charge are usually better nucleophiles than neutral analogs. So first one is basicity. Okay, let's say nucleophiles. We have nucleophiles which have negative charges. Are usually better nucleophiles. Nucleophiles as compared to their neutral species. Neutral analogs. Okay. So for example, I'm giving here analogs. For example, here say cis ethoxide C2H5O. Ethoxide is greater than hydroxyl group, greater than acetate, and then water. Okay. Negative charges are strong then, such as OH group greater than hydroxyl group is greater than neutral species water. Okay. So nucleophile which have negative charge on the group will have more nucleophilicity than the neutral species. Then this is another one criteria, another polarizability, and then another system is, another one is that one criteria here. Then if we go to the if we go to the periodic table, if it's grouped in the periodic table, nucleophilicity increases with increasing atomic size. So another criteria is that for each group in the periodic table, okay, nucleophilicity increases with increasing atomic size, with increasing atomic size. This is polarizability, okay, atomic size. This is polarizability of ability of electrons, okay. So this is another factor for nucleophilicity. So for example, iodide greater than bromide, greater than chloride, fluoride. Okay, another one is H2S, neutral species greater than water. Okay, so nucleophilicity greater like this. Okay, so these are depending on the periodic table group. Nucleophilicity increases with increasing atomic size. Another factor is about the steric basis. Also, steric factor also be there. Another criteria is about the steric factor. Okay, steric factor of the nucleophile. Steric factor is another factor. Okay, another criteria can reduce nucleophilicity. Nucleophilicity of large species. So here, for example, the superhydroxide ion is more basic than ethoxide ion, but the superhydroxide ion is TBU ethoxide ion is more basic than ethoxide ion. Okay, ONA or ethoxide ion, more basic. The superhydroxide ion is more basic than ethoxide ion, but the superhydroxide is a weaker nucleophile. This is weaker nucleophile. Usually, in basicity, usually the superhydroxide is greater than ethoxide, but the superhydroxide is a weaker nucleophile because its bulky groups prevents to form touching an electrophile. So these bulky groups, the superhydroxide weaker base because its bulky groups prevents from approaching to an electrophilic center. Okay, so this bulky group, ethoxide group prevents it from approaching an electrophilic center. Okay, electrophilic, that is due to the steric hindrance. Okay, electrophilic center. Yeah, as readily. So I'm repeating again. Steric factor is another factor for nucleophilicity. It is more bulkier, then nucleophilicity decreases. So for example, the superhydroxide is more basic than ethoxide group, but due to the bulkier groups of the ethoxy group, this is a weaker nucleophile. It's a weaker nucleophile because it cannot attack the electrophilic center very easily due to the steric hindrance of the nucleophile. Okay, these are factors we are discussing mostly about these. And living groups should be attached to a sp3 hybridized. So we have also discussed earlier. One group is that living groups should be attached to sp3. Okay, vinyl and phenols and halides do not undergo nucleophilic transition at the normal condition. Vinyl, so living groups should be attached to the sp3 saturated carbon system. That's why phenol and halides and then does not undergo this nucleophilic substitution reaction very easily to the normal conditions. So these are about the so this today let's take up this job. Okay, today after this we have discussed. So next class we'll do more detail about SN1, SN2, how they become okay. Okay, now today we will run up here.